Most galaxies are peaceful islands of stars, quietly spinning through the void for billions of years. But scattered across the cosmos are monsters, galaxies so violent, so extreme, so incomprehensibly destructive that they challenge everything we thought we knew about the universe. These aren't just big. They're cosmic killing machines, tearing apart neighboring galaxies, spewing radiation that would sterilize anything. Today, we're diving into the most lethal galaxies ever discovered. Cosmic threats that remind us the universe is not a gentle place, but a battleground where gravity, energy, and time wage war on scales that dwarf human comprehension. If you're fascinated by the extreme, violent side of the cosmos, make sure to subscribe to this channel and give a thumbs up. Now let's begin. To understand what makes a galaxy dangerous, we first need to grasp what galaxies normally are. Most galaxies are relatively stable systems containing billions or trillions of stars held together by gravity, rotating peacefully through space. The Milky Way, our home, is a typical spiral galaxy, beautiful, orderly, with new stars forming at a measured pace in its spiral arms. But not all galaxies are so calm. Some are cosmic outliers, systems where extreme physics creates conditions that would obliterate any life unlucky enough to be nearby. The first category of dangerous galaxies we'll explore are the active galactic nuclei, or AGN for short. At the heart of most galaxies sits a supermassive black hole, typically millions or billions times the mass of our Sun. In quiet galaxies like ours, these black holes are relatively dormant, occasionally snacking on gas or the rare unfortunate star. But in active galaxies, the central black hole is feeding voraciously, consuming massive amounts of material and releasing energy that outshines the entire galaxy's worth of stars. The process is violent beyond imagination. As matter spirals toward the black hole, it forms an accretion disk, a swirling maelstrom of gas heated to millions of degrees. Friction within this disk generates temperatures so extreme that the gas emits X-rays and gamma rays. Magnetic fields threading through the disk become twisted and amplified, channeling some of the infalling material into jets that shoot out perpendicular to the disk at nearly the speed of light. These jets can extend for millions of light years, punching through intergalactic space like cosmic blowtorches. The energy output is staggering. A single active galactic nucleus can emit more energy than 100 trillion suns. To put that in perspective, if an AGN were located where the nearest star system Alpha Centauri sits, about 4 light-years away, the radiation would be intense enough to strip Earth's atmosphere and sterilize our planet's surface in moments. Even at distances of thousands of light-years, the radiation environment around an AGN would prevent planets from developing or maintaining life as we know it. One of the most extreme examples is the galaxy Markarian 231, located roughly 600 million light-years from Earth in the constellation Ursa Major. Discovered by Armenian astronomer Benjamin Markarian in the 1960s, this galaxy harbors one of the most active, supermassive black holes we've ever observed. The black hole, with a mass estimated at 100 million times that of our Sun, is consuming material so rapidly that it produces a quasar, one of the brightest phenomena in the universe. Quasars are essentially AGN on steroids. The term is short for quasi-stellar radio source because when first discovered in the 1960s, astronomers thought they were looking at strange stars. Only later did we realize these impossibly bright points of light were actually the cause of distant galaxies, powered by supermassive black holes consuming matter at phenomenal rates. The most luminous quasars can be over 1,000 times brighter than the entire Milky Way galaxy, despite the energy coming from a region smaller than our solar system. The radiation from Markarian 231's core is so intense that it's actually blowing away the galaxy's own gas, the raw material needed to form new stars. Observations from the Hubble Space Telescope and other instruments show a superwind of hot gas streaming away from the galaxy's center at speeds exceeding 1,000 kilometers per second. This galactic-scale wind is carrying away roughly the mass of our Sun every single year, effectively performing a cosmic chemotherapy, killing the galaxy's ability to create new stars while trying to starve the black hole itself. But the black hole wins this battle. Even as it blows away the galaxy's gas, enough material continues falling inward to sustain the feeding frenzy. The jets emerging from Markarian 231's core extend for over 100,000 light-years, creating enormous bubbles of superheated gas that glow in X-rays and radio wavelengths. Any star system caught in the path of these jets would be subjected to radiation levels millions of times higher than anything Earth experiences, making life impossible. The Chandra X-ray Observatory, launched in 1999, has been instrumental in studying these violent systems. Its images of Markarian 231 reveal the intricate structure of the superwind and jets, showing how the black hole's energy carves cavities in the surrounding gas. These observations help astronomers understand not just individual galaxies, but how supermassive black holes shape galaxy evolution across cosmic time. Speaking of understanding our place in the cosmic hierarchy, if you want to grasp just how mind-bendingly insignificant we are compared to even a single galaxy, let alone these cosmic monsters, check out my video "You Won't Believe How Small We Are in the Milky Way," where we put our existence into perspective against galactic scales. The link is in the description below and pinned on the comments. Now let's explore an even deadlier type of galaxy. The second category of dangerous galaxies involves collisions. When galaxies crash into each other, the destruction isn't like two solid objects smashing together. Remember, galaxies are mostly empty space, with vast distances between stars. Instead, the danger comes from gravitational chaos. As two galaxies interpenetrate, their mutual gravity throws stars into wildly altered orbits. Close encounters between stars become far more common, potentially disrupting planetary systems. More dramatically, the collision compresses gas clouds, triggering explosive bursts of star formation. This might sound positive, more stars being born, but the flip side is that massive stars burn hot and die young, often exploding as supernovae within just a few million years. A galaxy in the throes of a major merger can experience supernova rates hundreds of times higher than normal. Imagine living in a galaxy where brilliant supernovae explosions occur not once per century, as in the Milky Way, but multiple times per year, scattered across the sky. The cumulative radiation from these explosions would create a hazardous environment across vast regions of the galaxy. The Antennae galaxies, catalogued as NGC 4038 and NGC 4039, provide a spectacular example of this collision violence. Located about 45 million light-years away in the constellation Corvus, these two spiral galaxies are currently in the midst of a massive merger. The collision began roughly 600 million years ago when complex life was just emerging in Earth's oceans, and will continue for hundreds of millions more years before the galaxies finally settle into a single elliptical galaxy. Hubble Space Telescope images of the Antennae galaxies are both beautiful and terrifying. The collision has stretched both galaxies into long tidal tails of stars and gas, creating the antenna-like structures that give them their name. Where the galaxies overlap, the compressed gas has ignited into thousands of brilliant star-forming regions, each birthing stars at prodigious rates. The combined Chandra and Hubble observations reveal over 100 X-ray sources in the collision zone, primarily binary star systems and supernova remnants, evidence of the violent stellar evolution happening in real time. But the Antennae galaxies, violent as they are, represent a relatively small-scale collision. For true cosmic carnage, we need to look at cluster-scale events. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies along with vast quantities of hot gas, the intracluster medium. When two clusters collide, the violence occurs on scales that dwarf individual galaxy mergers. The bullet cluster, officially designated as 1E0657-558, is one of the most famous examples. Located roughly 3.8 billion light-years away, this system shows two galaxy clusters that collided at speeds of around 4,700 kilometers per second, about 1.5% the speed of light. The collision happened roughly 150 million years ago, and we're seeing the aftermath. What makes the bullet cluster extraordinary isn't just the collision itself, but what it revealed about the universe's composition. When the clusters collided, the galaxies themselves, being mostly empty space, passed through each other relatively unscathed. But the hot gas that permeates each cluster, comprising most of the cluster's normal matter, collided and slowed down due to electromagnetic interactions. This created a separation between where the galaxies are and where the gas is. By using gravitational lensing, the way mass bends light from background galaxies, astronomers mapped where the total mass actually is. Shockingly, the majority of mass wasn't with the gas, but with the galaxies. This provided powerful evidence for dark matter, the invisible substance that dominates the universe's mass budget. The dark matter, which interacts only through gravity, passed straight through the collision without slowing down, following the galaxies. But from a danger perspective, the bullet cluster represents an extinction-level event on cosmic scales. The collision heated the intracluster gas to temperatures exceeding 100 million degrees Celsius. Any galaxy caught in the collision zone would be subjected to this superheated plasma, potentially stripping away its own gas and shutting down star formation. The shock waves generated by the collision would accelerate particles to extreme energies, creating a radiation environment hostile to life across millions of light-years. Now let's discuss the third category of deadly galaxies, starburst galaxies. These are systems undergoing star formation at rates far exceeding normal galaxies. While the Milky Way creates roughly 1 or 2 solar masses worth of new stars per year, starburst galaxies can produce hundreds or even thousands of solar masses annually. This might seem beneficial: more stars, more planets, more potential for life. But the reality is far grimmer. Starburst galaxies are creating predominantly massive stars which live fast and die explosively. The result is a galaxy saturated with ultraviolet radiation from young, hot stars, punctuated by frequent supernova explosions. The combined radiation and particle acceleration from these processes creates a galaxy-wide environment utterly hostile to life. M82, also known as the Cigar Galaxy, exemplifies this extreme star formation. Located approximately 12 million light-years away in the constellation Ursa Major, M82 is undergoing a starburst episode triggered by gravitational interactions with its larger neighbor, M81. The encounter has funneled enormous quantities of gas toward M82's center, igniting a stellar baby boom of epic proportions. The Hubble Space Telescope has captured stunning images of M82, revealing a galaxy literally tearing itself apart from the inside out. The intense star formation concentrated in the galaxy's core has generated a powerful galactic superwind, streams of hot gas being blown out perpendicular to the galaxy's disk at speeds exceeding 1,000 kilometers per second. This superwind extends for thousands of light-years above and below the galactic plane, visible as glowing filaments in optical and X-ray wavelengths. The Chandra X-ray Observatory's observations of M82 reveal over 200 extremely bright X-ray sources, many of which are young supernova remnants or black holes formed from massive stars that lived briefly and died violently. The galaxy's core is so dusty and active that it glows brilliantly in infrared light, detectable by the Spitzer Space Telescope as a region of furious stellar birth hidden behind veils of cosmic dust. Within M82's central regions, supernovae are exploding at a rate roughly 10 times higher than in the Milky Way. Every few years, another massive star reaches the end of its brief life and detonates, adding to the maelstrom of radiation and particle acceleration. Any planetary system in the galaxy's inner regions would be subjected to lethal radiation doses from multiple directions, with no safe haven from the constant bombardment. But starburst galaxies do more than threaten their own inhabitants. The superwinds they generate carry heavy elements, the products of stellar nucleosynthesis, far into intergalactic space. In this way, starburst galaxies act as cosmic polluters, enriching the intergalactic medium with metals while simultaneously rendering vast regions of their own territory uninhabitable. It's a cosmic paradox. The very processes that create the elements necessary for life make the galaxy lethal to that same life. The fourth category brings us to perhaps the most individually violent phenomena in the universe: galaxies hosting gamma-ray bursts. Gamma-ray bursts, or GRBs, are the most energetic electromagnetic events known, releasing more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. These cosmic explosions are thought to occur when the most massive stars, those exceeding perhaps 25 or 30 solar masses, reach the end of their lives and collapse directly into black holes. The collapse is catastrophic. Within seconds, a stellar core the size of a city collapses to a point, releasing gravitational potential energy that would power our civilization for billions upon billions of years if we could harness it. This energy drives jets of material outward along the star's rotational axis at velocities approaching the speed of light. When these jets break through the star's surface, they produce a gamma-ray burst, a focused beam of the most energetic photons possible, capable of sterilizing planets across an entire galactic arm. The galaxy NGC 253, located roughly 800 million light-years away, hosted a gamma-ray burst detected in 2003. Designated GRB 030329, this explosion lasted for only 23 seconds, but released energy equivalent to our Sun burning for its entire lifetime, compressed into less than half a minute. The Swift satellite, launched specifically to study gamma-ray bursts, caught the event and quickly relayed the coordinates to ground-based telescopes. Follow-up observations revealed a hypernova, a supernova even more powerful than normal, associated with the gamma-ray burst. The dying star, estimated to have had an initial mass of roughly 30 to 40 times that of our Sun, had collapsed and exploded with such violence that it outshone every other star in its galaxy combined. For a brief moment, this single stellar death was brighter than the billions of normal stars in the galaxy put together. The danger zone around a gamma-ray burst is enormous. Calculations suggest that a GRB occurring within our galaxy, even at distances of thousands of light-years, could have catastrophic effects on Earth if the beam happened to point our way. The gamma rays would slam into our upper atmosphere, triggering chemical reactions that would partially destroy the ozone layer. With diminished ozone protection, increased ultraviolet radiation from the Sun would reach the surface, potentially causing mass extinctions in the ocean's food chain and severe ecosystem disruption. Some scientists have speculated that the Ordovician-Silurian extinction event, which occurred roughly 445 million years ago and wiped out approximately 85% of marine species, might have been caused or contributed to by a gamma-ray burst. While we have no direct evidence for this hypothesis, the severity and pattern of the extinction is consistent with what we'd expect from a nearby GRB. The event affected primarily surface-dwelling ocean life, while leaving deeper creatures relatively unharmed, exactly what would happen if increased UV radiation penetrated the upper ocean layers. Fortunately, gamma-ray bursts are rare in our region of space. The Milky Way likely produces a GRB only once every few 100,000 to 1,000,000 years, and the odds of one pointing directly at Earth are extremely low. But in galaxies with higher rates of massive star formation, particularly starburst galaxies, GRBs occur far more frequently. Living in such a galaxy would mean existing under constant threat of sterilization from random stellar explosions. The fifth category of dangerous galaxies involves radio galaxies, systems where the central supermassive black hole launches jets so powerful they remain coherent across millions of light-years. These aren't the relatively modest jets from active galactic nuclei we discussed earlier. These are the cosmic equivalent of searchlights, beams of accelerated particles, and magnetic fields that dwarf entire galaxies. Cygnus A, despite being relatively nearby at roughly 600 million light-years distant, ranks among the most powerful radio galaxies ever discovered. First detected in 1939 and studied extensively since, Cygnus A harbors a supermassive black hole estimated at about 2.5 billion solar masses. This monster has launched jets that extend for about 300,000 light-years on either side of the galaxy, roughly 3 times the diameter of the Milky Way. The jets from Cygnus A aren't just streams of particles, they're cosmic cannons, accelerating matter to within a fraction of a percent of light speed. As these jets plow into the surrounding intergalactic medium, they create enormous lobes of radio-emitting plasma, visible to radio telescopes as structures that dwarf the visible galaxy. The total energy contained in these lobes is staggering, equivalent to converting roughly 10 million solar masses directly into energy through Einstein's famous equation E equals mc squared. The Very Large Array Radio Telescope in New Mexico has produced exquisite images of Cygnus A, revealing intricate structures within the jets and lobes. We see hotspots where the jets slam into surrounding gas, shock waves propagating through the plasma, and complex magnetic field structures threading throughout. The Chandra X-ray Observatory adds another layer, detecting X-rays from superheated gas, shocked by the jet's passage. Any galaxy unfortunate enough to lie in the path of Cygnus A's jets would face a cosmic catastrophe. The jets carry immense kinetic energy and contain particles accelerated to energies far beyond what Earth's atmosphere, or magnetic field, could shield against. Planets in the target galaxy would be bathed in high-energy particles and radiation capable of stripping atmospheres and sterilizing surfaces. Even at distances of hundreds of thousands of light-years from Cygnus A itself, being caught in the jet's path would be fatal to any civilization. The sixth category brings us to perhaps the most enigmatic dangerous galaxies, ultra-luminous infrared galaxies, or ULIRGs. These systems emit the majority of their light not in visible wavelengths, but in infrared, indicating the presence of enormous amounts of dust heated by violent processes occurring in their cores. ULIRGs are typically merger remnants, 2 or more galaxies that have collided and are in the process of combining into a single system. ARP 220, located approximately 250 million light-years away in the constellation Serpens, represents one of the nearest and best-studied ULIRGs. The Hubble Space Telescope reveals 2 galactic cores spiraling toward each other, surrounded by tidal tails of stars and gas stretched by gravitational forces. But the real action occurs in the cores, hidden behind thick veils of dust that absorb optical and ultraviolet light and re-radiate it as infrared. The Spitzer Space Telescope and the James Webb Space Telescope have pierced these dusty shrouds, revealing cores undergoing explosive star formation at rates exceeding 200 solar masses per year, over 100 times the Milky Way's rate. This starburst is fueled by the collision, which has funneled enormous quantities of gas toward the galaxy's centers. The infrared luminosity of ARP 220 exceeds 100 billion times the Sun's luminosity, with most of this energy coming from regions smaller than a few hundred light-years across. But star formation isn't the only power source. Deep within ARP 220's dusty cores lurk two supermassive black holes, the remnants of the merging galaxy's central black holes. These black holes are also feeding, consuming gas and dust, while generating additional energy. X-ray observations from NuSTAR, the Nuclear Spectroscopic Telescope Array, have detected high-energy X-rays characteristic of materials spiraling into black holes, confirming that both starburst and active galactic nucleus activity contribute to the system's extreme luminosity. The environment within a new large like ARP 220 is perhaps the most hostile in the universe. Radiation levels are extreme across all wavelengths. The density of stars is far higher than in normal galaxies, increasing the odds of gravitational perturbations disrupting planetary orbits. The gas and dust that fuel the activity also obscure any potential sunlight, creating a dark, smothered environment despite the furious energy generation. If hell had a cosmic equivalent, it might resemble the core of an ultra-luminous infrared galaxy. Our seventh category of dangerous galaxies involves those harboring intermediate mass black holes that have gone rogue. While supermassive black holes typically remain anchored at galactic centers, intermediate mass black holes, ranging from hundreds to hundreds of thousands of solar masses, can form through different processes and potentially wander through galaxies. These roaming black holes are cosmic hazards in their own right. Simulations show that a wandering intermediate mass black hole passing through a galaxy can gravitationally disrupt star clusters, fling stars into altered orbits, and potentially trigger star formation by compressing gas clouds it encounters. More ominously, if such a black hole passed through a planetary system, the gravitational perturbations could eject planets from their orbits or send them spiraling into their star. The galaxy ESO 243-4, roughly 750 million light-years distant, shows evidence of hosting a wandering intermediate mass black hole. Observations from the Hubble Space Telescope and Chandra X-ray Observatory detected an unusually bright X-ray source offset from the galaxy's center, moving through the galactic disk. The source's properties, its X-ray spectrum, variability, and velocity suggest it's a black hole of roughly 50,000 solar masses, plowing through the galaxy at several hundred kilometers per second. Such wandering black holes might be more common than we realize. They could form when smaller galaxies merge with larger ones, with the smaller galaxy's central black hole surviving the merger but being kicked away from the new, combined core. Gravitational wave emissions from asymmetric black hole mergers could also impart momentum kicks, sending merged black holes careening through their host galaxies. The eighth category brings us to galaxies in the process of self-destruction, systems where the central black hole's energy output is so extreme that it's blowing the galaxy apart. These are the most dramatic examples of AGN feedback, the process by which supermassive black holes regulate their host galaxy's growth. SDSS J1255+0747, discovered through the Sloan Digital Sky Survey, represents an extreme case. This galaxy, located roughly 4.4 billion light-years away, hosts a quasar so powerful that it's launched winds traveling at roughly 8,000 kilometers per second, nearly 3% the speed of light. These winds aren't confined to narrow jets, but emerge as a wide-angle outflow that sweeps across much of the galaxy. The Gemini Observatory and Keck Observatory spectroscopic observations reveal these winds carrying away roughly 400 solar masses of gas per year, far more than the galaxy can replace through normal processes. At this rate, the galaxy will exhaust its gas supply within a few tens of millions of years, effectively sterilizing itself. Star formation will cease. The galaxy will fade to a collection of aging stars, unable to create new generations. But before that happens, the galaxy experiences a period of extreme violence. The winds compress gas ahead of them, potentially triggering star formation, even as they remove the raw material needed to sustain it. The radiation environment from the quasar, combined with the kinetic energy of the winds, creates conditions lethal to any life that might have existed in the galaxy's inner regions. This is cosmic euthanasia, the black hole killing its host while simultaneously committing suicide by starvation. The James Webb Space Telescope has begun studying these extreme outflow systems in unprecedented detail. Its infrared vision can peer through the dust that often obscures quasars, revealing the interaction between the outflows and the surrounding galaxy. Early observations show complex structures, cavities carved by the winds, shocked gas glowing in specific emission lines, and evidence of star formation both triggered and suppressed by the outflow's passage. Our ninth category involves galaxies caught in the crossfire of cosmic rays. Cosmic rays are high-energy particles, primarily protons, accelerated to velocities approaching the speed of light by energetic processes throughout the universe. Supernova remnants, pulsar winds, and active galactic nuclei all contribute to the cosmic ray background. But some galaxies experience cosmic ray bombardment far exceeding the norm. NGC 1068, a starburst galaxy located roughly 160 million light-years away, provides an extreme example. This galaxy's vigorous star formation produces numerous supernovae, each accelerating particles to extreme energies. The Fermi Gamma Ray Space Telescope has detected gamma rays from NGC 1068, photons produced when cosmic ray protons collide with interstellar gas, creating particles that decay into gamma rays. The cosmic ray energy density in NGC 1068 is estimated to be roughly 100 times higher than in the Milky Way. This intense cosmic ray bath has profound implications. Cosmic rays damage DNA and other organic molecules. Earth's atmosphere and magnetic field shield us from most cosmic rays, but in NGC 1068, the radiation environment would penetrate much deeper into any atmosphere. Surface life would face mutation rates potentially incompatible with complex organisms. Moreover, cosmic rays affect gas chemistry, breaking apart molecules and ionizing atoms. This impacts the ability of gas clouds to cool and collapse to form new stars. In galaxies with extreme cosmic ray pressures, the very process of star formation can be altered. The cosmic rays might even help drive galactic winds, adding their pressure to the thermal pressure from supernovae to blow gas out of the galaxy. The Cherenkov telescope array, currently under construction, will eventually provide even more detailed studies of high-energy processes in galaxies like NGC 1068. By detecting very high-energy gamma rays, this next-generation observatory will map the acceleration and propagation of cosmic rays through galactic environments, helping us understand just how deadly these energetic particles make certain galaxies. Our 10th category examines tidal disruption event hosts, galaxies where we've observed supermassive black holes shredding stars. When a star passes too close to a supermassive black hole, tidal forces, the difference in gravitational pull across the star's diameter, can exceed the star's own gravity holding it together. The result is catastrophic. The star is torn apart in a process astronomers call spaghettification. The galaxy RxJ1242-1119, located roughly 700 million light-years away, hosted one of the most dramatic tidal disruption events ever observed. In 2011, the Pan-STARRS telescope in Hawaii detected a sudden brightening, a star being ripped apart by the galaxy's central black hole. The event was designated PS110J as the star was shredded. Roughly half its material was flung into space at high velocity, while the other half was captured by the black hole, forming a temporary accretion disk. The infalling stellar debris released gravitational potential energy as it spiraled inward, heating to millions of degrees and emitting X-rays and ultraviolet light. The event brightened dramatically over a period of weeks, temporarily making the galaxy's core as bright as millions of suns, before fading over several months as the debris was consumed. The SWIFT satellite, along with ground-based telescopes, monitored this event across multiple wavelengths. The observations revealed jets of material being launched from near the black hole, similar to but less powerful than the jets from active galactic nuclei. Spectroscopic analysis showed the stellar debris, primarily hydrogen and helium, the outer layers of what was likely a sun-like star, being accelerated to thousands of kilometers per second. These tidal disruption events remind us that supermassive black holes are patient hunters. They sit at galactic centers waiting for stars to wander too close. In a typical galaxy like the Milky Way, such events might occur only once every 10,000 to 100,000 years. But in denser galactic cores, particularly in the aftermath of galaxy mergers, when stellar orbits are disrupted and randomized, tidal disruption rates can increase dramatically. Living in a galaxy with frequent tidal disruptions would mean witnessing periodic flare-ups from the galactic core, sudden increases in radiation that could have impacts across the galaxy. While planets orbiting stars thousands of light-years from the core would likely be safe from direct harm, the psychological impact of witnessing your galactic center periodically devouring stars would be profound. The 11th category brings us to perhaps the most ominous, dangerous galaxies, those containing supermassive black hole binaries. When two galaxies merge, their central supermassive black holes eventually sink to the center of the merged galaxy through dynamical friction. But rather than immediately combining, they can orbit each other for millions or even billions of years, creating a binary supermassive black hole system. OJ287 is one of the best candidates for hosting such a binary. This blazar, a type of active galactic nucleus with jets pointed nearly directly at Earth, shows periodic variations in brightness that some astronomers interpret as evidence for a binary black hole system. Located roughly 3.5 billion light-years away, OJ287's central engine might consist of two supermassive black holes, each weighing billions of solar masses, orbiting each other every roughly 9 years. Binary supermassive black holes are dangerous for multiple reasons. First, their gravitational influence can fling stars throughout the galaxy into altered orbits, a process called the gravitational slingshot. Some stars gain so much energy they're ejected from the galaxy entirely, becoming intergalactic wanderers. Others are sent plunging toward the galactic center, potentially being destroyed by tidal forces. Second, the orbital motion of the black holes generates gravitational waves, ripples in space-time itself. While we can't yet detect gravitational waves from such systems, they oscillate at frequencies too low for current detectors like LIGO. Future space-based observatories like the Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will be able to detect these signals. The gravitational wave energy carries away orbital energy, causing the black holes to gradually spiral closer together. When binary supermassive black holes finally merge, the event releases tremendous energy in gravitational waves. Calculations suggest such mergers could release energy equivalent to converting several solar masses directly into gravitational radiation in a matter of minutes. The space-time ripples from these mergers would be detectable across the observable universe. Any civilization close enough to witness the final merger up close would experience space-time itself shaking, though the effects on matter would likely be subtle, except at extremely close range. Our 12th category examines galaxies undergoing ram pressure stripping, systems being violently torn apart by their motion through intergalactic gas. This primarily occurs in galaxy clusters, where the space between galaxies isn't empty, but filled with hot, diffuse plasma at temperatures of millions of degrees. ESO 137-001, also known as the Jellyfish Galaxy, provides a spectacular example. This spiral galaxy is falling through the Abell 36-27 cluster at roughly 2,000 kilometers per second. As it plows through the intra-cluster medium, the ram pressure, like wind resistance, but from gas instead of air, strips gas from the galaxy's disk, creating long tentacles of star-forming material trailing behind like a jellyfish's tentacles. The Hubble Space Telescope and ALMA, the Atacama Large Millimeter Array, have revealed the details of this cosmic violence. Star formation is occurring not just in the galaxy's disk, but along the stripped tentacles, creating chains of bright young star clusters stretching for tens of thousands of light years. Yet this star formation is a last gasp. Once the gas is fully stripped, star formation will cease and the tentacles will fade as their stars age. Ram pressure stripping effectively strangles galaxies, cutting off their supply of star-forming material. Living in a galaxy undergoing this process would mean witnessing the gradual death of your cosmic home. New stars would eventually stop forming. The interstellar medium would be swept away. The galaxy would slowly redden as hot blue stars died and weren't replaced, until only long-lived red dwarfs remained, orbiting in an increasingly empty galactic disk. The 13th category involves galaxies hosting soft X-ray transients, binary systems where a black hole or neutron star accretes material from a companion star in violent, irregular outbursts. While individual transient events occur in many galaxies, including our own, some galaxies show unusually high rates of these explosions. M31, the Andromeda Galaxy, our nearest large galactic neighbor at roughly 2.5 million light-years distant, hosts an unexpectedly large population of X-ray transients. Chandra X-ray observatory observations have catalogued dozens of these systems, far more than expected for a galaxy of Andromeda's type. Some are recurrent transients, flaring up every few years or decades as material from the companion star periodically overwhelms the accretion disk and falls onto the compact object. These transients, while individually less energetic than supernovae, create local radiation hazards. The X-rays they emit can affect nearby star systems, potentially stripping planetary atmospheres if the systems are close enough. More concerningly, some models suggest that black hole X-ray transients might occasionally launch jets similar to but less powerful than those from active galactic nuclei. A planetary system caught in such a jet's path would face a brief but intense radiation bath. The prevalence of X-ray transients in Andromeda raises questions about our own future. In roughly 4 to 5 billion years, the Milky Way and Andromeda will collide and merge. The merger will create a new galaxy, sometimes nicknamed Milkomeda, that will likely host an even higher rate of X-ray transients as stellar orbits are disrupted, creating new close binary systems. Any civilization surviving the merger will inherit a galaxy more dangerous than either of its progenitors. Our 14th category examines galaxies with runaway nuclear fusion, systems where chain reactions in stellar interiors might be occurring on galactic scales. While this sounds like science fiction, recent observations suggest that under extreme conditions, star formation itself can become a runaway process. Goods N774, a galaxy observed in the Goods North Field at a distance of roughly 12 billion light-years, shows evidence of star formation occurring at an almost incomprehensible rate. The James Webb Space Telescope's observations reveal this galaxy forming stars at a rate exceeding 1,000 solar masses per year, roughly 500 to 1,000 times the Milky Way's rate. At such extreme star formation rates, the galaxy is converting its entire gas supply into stars in just a few tens of millions of years. The energy output is staggering. The young star's ultraviolet radiation, the supernova explosions from short-lived massive stars, and the collective stellar winds are pumping energy into the interstellar medium at rates that should blow the galaxy apart. Yet somehow the galaxy is holding together, at least temporarily. The physics of such extreme starbursts remains poorly understood. How does gas continue collapsing into new stars when the energy from existing stars should heat and disperse it? Why doesn't the starburst blow itself out immediately? These questions drive current research, with implications for understanding how galaxies evolved in the early universe when such extreme starbursts were more common. Living in a galaxy undergoing a runaway starburst would be surviving in a cosmic forge. The sky would be filled with brilliant young stars, making nights far brighter than on Earth. But this beauty would come at deadly cost. Radiation levels would be extreme. Supernovae would explode constantly. Any planetary atmosphere would be subjected to continuous bombardment by stellar winds and high-energy particles. Complex life would likely be impossible across most of the galaxy. The 15th category brings us to galaxies hosting hypervelocity stars, stars moving so fast they're escaping the galaxy entirely. These stellar cannonballs, traveling at speeds exceeding 1,000 kilometers per second, are thought to be produced primarily by interactions with supermassive black holes. When a binary star system wanders too close to a galactic center's black hole, tidal forces can tear the binary apart, sending one star plunging into the black hole while the other is flung away at tremendous velocity. The galaxy SDSS J09074 5+5 12349 shows evidence of having ejected numerous hypervelocity stars. Spectroscopic surveys searching for these stellar refugees have identified several stars moving away from this galaxy at velocities exceeding 2,000 kilometers per second, far faster than the galaxy's escape velocity. Tracing these stars' trajectories backward in time points to the galaxy's core as their origin. Hypervelocity stars pose an unusual danger. Imagine living on a planet orbiting a star that suddenly accelerated to escape velocity by a black hole encounter. Your entire solar system would be flung into intergalactic space, leaving your galaxy behind. Over millions of years, the galaxy would fade from view as your star careened through the void between galaxies. Your descendants would be cosmic orphans, forever separated from their galactic home. More immediately threatening, the process that creates hypervelocity stars, close encounters with supermassive black holes, would subject any planets orbiting those stars to tremendous gravitational stresses. Planetary orbits could be disrupted or destabilized. The stellar companion falling into the black hole would likely produce a tidal disruption event, bathing any surviving planets in the system with intense radiation before the star's destruction. Our 16th category examines galaxies hosting magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. While magnetars exist in the Milky Way, some galaxies host unusually high populations of these magnetic monsters, likely due to high rates of massive star formation and peculiar stellar evolution pathways. The small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way at roughly 200,000 light-years distance, hosts a surprising number of magnetars given its relatively small size and mass. Observations from the Swift satellite and the Fermi Gamma Ray Space Telescope have detected several magnetar giant flares from this galaxy, brief but incredibly intense bursts of X-rays and gamma rays. A magnetar giant flare releases more energy in a fraction of a second than the Sun emits in thousands of years. The most powerful flare ever detected from SGR 1806-20 released roughly 10 to the 46 ergs in 0.2 seconds, equivalent to the Sun's total energy output for roughly 150,000 years, compressed into a fraction of a heartbeat. If a magnetar flare occurred within a few thousand light-years of Earth, the consequences would be severe. The X-rays and gamma rays would ionize Earth's upper atmosphere, potentially destroying much of the ozone layer. The energetic particles would create a cascade of secondary radiation. Satellite electronics would be damaged or destroyed. The event could trigger a mass extinction by allowing increased ultraviolet radiation from the Sun to reach Earth's surface. Living in a galaxy with a high magnetar population would mean existing under constant threat of these radiation storms. Unlike supernovae, which give some warning as massive stars approach the end of their lives, magnetar flares are unpredictable. A civilization could have no warning before their planet was bathed in lethal radiation from a flare in a nearby stellar neighborhood. The 17th category involves galaxies caught in gravitational lensing configurations that amplify their dangerous output. Gravitational lensing occurs when a massive object's gravity bends light from a more distant source, sometimes creating multiple images or magnifying the background object's brightness. The galaxy cluster, MAX J0, 717.5 plus 3745, contains a background galaxy that's gravitationally lensed into multiple images, but this particular background galaxy also happens to be an active starburst with a powerful AGN. The lensing magnifies both the AGN's output and the starburst's emission, creating an apparent brightness far exceeding what the galaxy would display without lensing. This has allowed astronomers to study this dangerous galaxy in unprecedented detail despite its extreme distance of roughly 12 billion light-years. The James Webb Space Telescope has observed this system, revealing the fine structure of star-forming regions and the AGN's influence on its host galaxy. The observations show that the AGN is driving winds that compress nearby gas, triggering star formation even as they blow away material. But imagine if such a lensing configuration occurred with a nearer, more immediately threatening galaxy. A quasar's beam, normally dangerous within its galaxy and for some distance beyond, could be gravitationally focused by a foreground lensing mass. The lensing wouldn't add energy, but it could concentrate the radiation into a tighter beam, creating a cosmic death ray of sorts. While such configurations are rare, they're not impossible. The 18th category brings us to galaxies hosting intermediate luminosity optical transients, stellar explosions more powerful than novae, but less energetic than supernovae. These events, sometimes called ilots, remain poorly understood, but observations suggest they might result from stellar mergers or from stars being tidally disrupted by smaller black holes than those found at galactic centers. M85, a lenticular galaxy roughly 60 million light-years away in the constellation Coma Berenices, hosted a remarkable ilot designated M85 OT 2006-1. This event brightened dramatically over several weeks in 2006, reaching a peak luminosity roughly 1 million times that of the Sun before fading over months. The Hubble Space Telescope and ground-based observatories monitored this event's evolution. Spectroscopic observations revealed outflows of material moving at thousands of kilometers per second. The energy release exceeded that of any nova but fell short of supernova levels. The leading theory suggests two stars merged, briefly releasing tremendous energy as their merger drove explosive nuclear burning. If ilots are common in certain types of galaxies, perhaps those with high stellar densities where stellar encounters and mergers are more frequent, they would create an additional hazard layer. While less energetic than supernovae, islets are likely more common, creating a galaxy where stellar explosions of varying intensities occur regularly, maintaining a high background radiation environment. The 19th category examines galaxies with unusual amounts of primordial gas, hydrogen, and helium from the Big Bang that hasn't been enriched by stellar nucleosynthesis. Some distant galaxies observed by the James Webb Space Telescope show surprisingly high fractions of primordial gas, suggesting they've avoided the normal recycling processes that enrich galaxies with heavy elements over time. These chemically primitive galaxies might seem less dangerous, but the opposite could be true. Stars forming from primordial gas with very low metallicity tend to be more massive on average than stars forming from enriched gas. More massive stars burn hotter, live shorter, and die as more energetic supernovae. A galaxy dominated by first-generation stellar populations would experience higher supernova rates and more intense radiation than a chemically evolved galaxy. Moreover, low metallicity stars produce different stellar remnants. They're more likely to collapse directly into black holes rather than exploding as supernovae, potentially creating larger populations of stellar mass black holes. Some of these black holes might form binary systems, eventually merging and releasing gravitational waves. A chemically primitive galaxy could be a black hole factory, churning out these cosmic singularities at higher rates than normal. The 20th category involves galaxies in the process of being evaporated by high-energy radiation from neighboring quasars. This process, called photoevaporation, occurs when a powerful radiation source heats a nearby galaxy's gas to temperatures exceeding the galaxy's gravitational binding energy. The quasar HE 0450-2958, located roughly 12 billion light-years away, appears to be evaporating a neighboring galaxy. The quasar's ultraviolet output, amplified by its active accretion disk, is heating the nearby galaxy's gas to temperatures of tens of thousands of degrees. At these temperatures, the gas has enough energy to escape the smaller galaxy's gravitational pull. Observations from the Keck Observatory and the Very Large Telescope show streaming motions in the neighboring galaxy's gas, directed away from the quasar. Over tens of millions of years, this photoevaporation will completely strip the galaxy of its gas, leaving behind a dead stellar remnant, a galaxy that can no longer form stars, slowly fading as its existing stars age and die. Living in a galaxy being evaporated would be witnessing a slow-motion apocalypse. The night sky would be dominated by the brilliant quasar, outshining everything else combined. The galaxy's gas, the raw material for new stars and the medium that provides cosmic ray shielding, would be streaming away into intergalactic space. Any atmosphere on any planet would face intense ultraviolet radiation from the quasar, potentially being slowly stripped away by the same photoevaporation process, destroying the galaxy itself. Our 21st category examines galaxies hosting unusually large populations of Wolf-Rayet stars, extremely massive stars that have shed their outer hydrogen layers, exposing their helium cores. These stars burn ferociously hot, with surface temperatures exceeding 50,000 Kelvin, and pump enormous amounts of energy into their surroundings through intense stellar winds. NGC 303, located roughly 12 million light-years away in the constellation Leo, contains an exceptional concentration of Wolf-Rayet stars in its central starburst region. Spectroscopic observations reveal dozens of these stellar behemoths packed into a region only a few hundred light-years across. Each star is losing mass at rates of roughly 1/10,000,000th to 1/1,000,000th of a solar mass per year, creating powerful stellar winds that collectively reshape the galaxy's interstellar medium. The combined wind power from NGC 303's Wolf-Rayet population exceeds 10 to the 42 ergs per second, equivalent to 10 million suns' total luminosity being pumped into the interstellar medium purely as kinetic energy. This drives a superwind that extends thousands of light-years beyond the galaxy's disk, creating a bubble of hot gas visible in X-ray observations. But Wolf-Rayet stars don't just blow wind, they're ticking time bombs. These massive stars are near the end of their lives and will explode as supernovae within a few million years. In NGC 303, this means multiple supernovae per century, creating a continuous bombardment of shock waves and high-energy particles. Any planetary system in the galaxy's central region would face radiation levels incompatible with life. The 22nd category brings us to galaxies with runaway black hole growth, systems where the central supermassive black hole is gaining mass so rapidly that it's growing noticeably even on human timescales. While black holes grow slowly under normal circumstances, certain conditions can trigger episodes of hyperaccretion. The galaxy CID-42, discovered in the Cosmic Evolution Survey field at a distance of roughly 4 billion light-years, shows evidence of a supermassive black hole growing at near-theoretical maximum rates. The black hole, estimated at several billion solar masses, is accreting material at roughly the Eddington limit, the maximum rate at which a black hole can sustain accretion before radiation pressure from the infalling material halts further accretion. At this growth rate, the black hole is gaining roughly 10 solar masses per year. This might not sound like much compared to a billion solar mass black hole, but it represents a growth rate of roughly 1% per 10 million years. Over cosmic timescales, such growth rates can build supermassive black holes from intermediate mass seeds in relatively short periods. The danger comes not from the growth rate itself, but from what it implies. To sustain such rapid accretion requires enormous amounts of gas funneling toward the galactic center. This gas forms a thick, turbulent accretion disk that generates intense radiation, winds, and potentially jets. The environment within the central few thousand light-years of CID-42 would be extraordinarily violent, with gas temperatures exceeding millions of degrees and radiation levels lethal to any form of life. The 23rd category examines galaxies hosting micro-quasars, stellar mass black holes with jets, essentially miniature versions of quasars. While individual micro-quasars exist in many galaxies, some systems show unusually high populations of these objects. IC10, a member of the galaxy pair nicknamed ARP-299, contains several confirmed microquasars despite its relatively small size. Observations from the Very Large Array and the Chandra X-ray Observatory have detected radio and X-ray emission characteristic of jet activity from stellar mass black holes accreting from companion stars. Microquasar jets, while far less powerful than quasar jets, still carry significant energy. They accelerate particles to relativistic speeds and generate radiation across the electromagnetic spectrum from radio to gamma rays. A planetary system in the path of a microquasar jet could experience increased radiation, though the effect would be far more localized than from a quasar, dangerous primarily within hundreds or thousands of light-years rather than millions. The danger of galaxies with high microquasar populations isn't so much the individual objects as the cumulative effect. Each microquasar contributes to the galaxy's high-energy radiation background. Together they accelerate cosmic rays, heat the interstellar medium, and create a network of radiation hazards throughout the galaxy. Our 24th category involves galaxies undergoing tidal heating, systems where gravitational interactions with neighbors are pumping energy into the galaxy, heating its gas and potentially driving star formation. This process can transform relatively quiet galaxies into violent starbursts. M51, the famous Whirlpool galaxy located roughly 23 million light-years away, is undergoing tidal heating from its smaller companion, galaxy NGC 5195. The gravitational interaction has triggered dramatic spiral arm enhancement in M51 with brilliant star-forming regions tracing the spiral pattern. Hubble Space Telescope images reveal thousands of young star clusters along the spiral arms, evidence of the ongoing starburst. But this beauty comes at a price. The tidal heating is also generating turbulence in M51's interstellar medium, creating shock waves that accelerate cosmic rays and heat the gas. Supernova rates have increased as the newly formed massive stars reach the end of their brief lives. The galaxy is being simultaneously created and destroyed by its interaction with its smaller companion. In a few 100 million years, NGC 5195 will likely merge completely with M51, triggering an even more violent starburst. The merged system will experience a period of extreme star formation before settling into a new equilibrium. Any civilizations in either galaxy would witness their cosmic environment transformed over timescales of millions of years, slow by human standards but rapid on cosmic timescales. If you made this far, make sure to subscribe to the channel and give a thumbs up. If you enjoyed this video, I am sure you will love this other one at the left side of the screen. This is why we will never leave the Milky Way. In this video, discover the real science behind our cosmic confinement and why intergalactic travel is impossible, not just for us, but for any civilization. See you there.